All right, so the first section we're going to look at this week, as I said, is 3.7. It's pretty quick. It's just solving systems of equations graphically, which basically means finding where two graphs cross each other. And depending on how complicated the graphs are, you can have more than one intersection point. Obviously, if you just have two lines, you won't. But if you have like a parabola and a line, you might have two. Okay, so a system of equation is basically when you have to solve two or more equations for two or more variables. Generally, the equations we're going to stick with will have exactly two equations and two variables. But sometimes you have equations with 3 variables, 5 variables. You can have as many variables as you want. Okay, and there's different algebraic methods to solve. We're not going to be doing those today, but algebraic, you've got substitution, you've got elimination. You can use a matrix if you did that in Algebra 2. A matrix or matrices, that's the best way to solve systems when they start to get more complicated. Graphing certainly isn't. Okay, graphing in 2D is okay, but if you start getting more variables, like 3 variables, now you're in 3D. So now you have to find where things cross in 3D. And we can't graph in 3D. So graphing is not the best solution when you start to get more and more complicated, but it's okay for 2D because we can graph it. Okay, so when you have 2 variables and you're solving it, the solution is a coordinate. Okay, it's an ordered pair. Okay, so remember, you're looking for 2 values. You're looking for an x value and a y value when we solve a system. Or it could use letters other than x and y. It could use a and b, but the point is you're looking for 2 values. Okay. In order to solve a system graphically, the best way to probably do it is with a graphing calculator. If you're trying to graph on graph paper by hand and see where 2 things cross, what could go wrong graphing by hand and using graph paper to try to see where 2 graphs cross? Okay, you might not be exact. It could be really hard if it's a decimal. Like if the x value and where it crosses is like 1.6, you're not going to be able to figure that out when you graph by hand. Right? It's going to be really hard to guess that. Okay, but graphing combined with the calculator makes it really pretty doable. Okay, so any questions on what we're going to look for when we graph? Okay, now in order to type something in on the graphing calculator, what variable do you have to get by itself? Y. So this assumes that you have an equation that you can solve for y. There are some equations where you can't isolate the variable. If I gave you something like this, just as an example, and I said to get x by itself, or change those to y's, and get y by itself, you can't. That's not an equation where you can isolate the variable. And the problem is because it's in an exponent and it's over here too. Okay? And you can look it up. It's just not possible to solve this with regular algebra methods. Okay? So the equations I give you, you will be able to get the variable by itself. All right, so let's look at this one. All right, so it asks us to solve this graphically. Okay, by quickly looking at each equation, when you graph these, what kind of shape are they both going to be? Yep. Yeah, they're both linear. Okay, you don't have any squared, no variables that are squared, so you're not going to get parabolas. So we have 2 lines. Let's rewrite them with y by itself. Okay, and what would you get if you rewrite that first equation and get y by itself? Yep.
2x plus 5 would be 3.
Yeah, we don't, careful though, it wouldn't be a positive 2x.
Oh, negative 6.
Yeah, you'd have to subtract the 2x. And in the end, you'd have to divide by 3. So I'm going to write that as my slope. And, oh yeah, plus 5. Don't forget that. And you would also have divided that by 3. Hey, any questions on that? Just minus the 2x and divide by 3. Okay, for this one, this time I would add the 3x, and then I would divide by what number? Okay, 5. So I'm going to have, when I add the 3x, it's going to become a positive 3x, and then I'm going to divide it by 5. And I still have that 21 on the other side, and that also gets divided by 5. Now, how can I guarantee you that those lines are going to cross before I even graph them? Because some lines don't cross each other, but I know these will. Yeah?
Well, they're not parallel to each other.
Right, they're not parallel. How do you know they're not parallel? What tells you that?
Their slopes are different.
Yeah, the slopes are different. So because we have different slopes, they're going to cross each other. Okay, and the way I typed in that slope, that's fine. You can just put the x on the top, or you could do it differently, but that's just faster for me to type that way. Okay, so negative 2/3 x plus 5/3, and
Do you always have to put in parentheses?
you might be able to get away without doing it, but I'm afraid it would like add something to the denominator of the slope. So if I do it that way, I know it won't do anything funny. All right, so let's graph them. And I'll start with a standard window and see if we can tell where they cross. Okay, I'm guessing it looks like it's about negative 2, 3. I'll just calculate that exactly. So how do I find where they cross? What do I press? Yep.
Second calc.
Second calc, and which option?
Intersect.
Intersect. Is the guess going to matter here?
No.
No, because there's only one on the screen one point where they cross. So just pick anywhere on the blue, anywhere on the red, and you can put the guess anywhere you want. And it says they do cross at the point negative 2, 3. Okay. So you can write your answer that way, or you can write it this way. Same thing. But all you have to do is use the calculator. Any questions on that? I was going to try to put the picture there so you could see it, but apparently I can't. All right. How about this one? Is this going to be linear? No. Okay, these are polynomials, but I have a cubic and a parabola, quadratic. So a cubic and a quadratic, they could intersect all kinds of ways. Actually, this cubic, because of the negative in front, is going to look more like that. And if I draw a parabola through there, how many times could the parabola cross that cubic? I do the same thing twice. How many times can a parabola cross that cubic? I could definitely get twice out of that. Yep. Could I get more than 2 times? Yeah. If I had a parabola just like that. Could cross up to 3 times. Okay, so let me graph it and see what I'm looking at. And again, actually, because of this negative in front, the parabola is going to open down. So we're going to get a picture that looks something kind of like that. Okay, just as a rough guess, I don't exactly know where the parabola is, so I don't know if it's just going to cross once, twice, or 3 times. But I do know it opens down. All right, so let's graph our parabola. It's negative x cubed plus 3x squared plus x minus 3. And negative 2x squared plus 5. Okay, so there's my cubic with the general kind of behavior I tried to show you. And our parabola is coming. All right. So how many times do those cross?
2.
Twice?
Well, 2 in the picture,
2 in the picture, yep.
but below it, probably across it again.
You think it's going to cross a third time?
Yeah.
Yeah, because that, I can tell that red line does look like it's getting closer. So if you wrote 2, in this case, it's actually going to be 3. So set your y min to like negative 40. I'm just guessing. This is going to make the other 2 intersection points harder to see, but I already know that it, actually you can still see it pretty good. And actually this one, I'm not sure I can quite see where they cross yet, but I can definitely tell they're going to cross a third time. Okay, so this question just said find the number of solutions to the system, and it's 3. Okay, any questions on that one? If you wanted all 3, you just have to do second calc intersect 3 times. All right, so I think this is the last. Yeah, this will be our last one for this section. All right, so we're going to solve this one graphically and algebraically. Let's do it algebraically first. What method would I use to solve this algebraically? How would I start? I have y equals x cubed minus x and y equals 3x. Any ideas what we would do to solve that? One of the methods I mentioned algebraically is what you would do here. Oh, Allie? Any thoughts?
I'd probably do elimination. But
Do elimination? Okay, you could do elimination, or you could try to, but this one's already set up to do another method because of the way the problem is written. It's set up very nicely to do something.
Would you plug y in for y?
Yeah, do substitution. Okay. Take what y is equal to and plug it in. So x cubed minus x equals 3x. Now what would you do, Dave?
Subtract x from, or add x to both sides.
Okay, you can add x to both sides. I do like the idea of combining the x's, but what I think I would do is get all the x's on one side. If you add x, it's going to leave them on both sides.
Okay, so subtract 3x.
Let's subtract 3x. Now we've got it equal to 0, which is always a good thing, because if we can factor that, then we can solve it. What can I factor out of x cubed minus 4x? Yeah. Factor out of x. And what can I do now? That's a difference of 2 what? Difference of 2 squares. Right, so x squared minus 4, how does that factor? Yeah.
x plus 2 and x minus 2.
Very good. X plus 2, x minus 2. Now I can get my 3 answers. And in this case, they're all real. There are no imaginary answers here. So what are my roots here? Negative 2, yep. Positive 2? At 0. Okay, so positive or negative 2. And 0. All right, so let's graph that and see if we get the same thing. Okay, of course, we should. So we get x cubed minus x and 3x. Now I know a standard window should work okay. I found my x values. I still need to find my y values. Okay, so I know my x values are at negative 2, 2, and 0. So let's write that. Now that I get the x values, how do I get the y values? Just plug them in for x. So the quickest one, I think, is just to take your x value, triple it, and that's your y value. So what's negative 2 tripled? 2 tripled? And 0 tripled? So those should be the 3 points of intersection. Okay, I'll just, I'll calculate one of them. Does the guess matter here?
Yes.
Yeah. It depends, whichever one you're closest to, that's the one it'll give you. So I think I can tell it crosses through the origin, but let me try this one. 2, 6. Yep, there's one of my points. And if you do the other ones, you'll get negative 2, 6, and 0, 0. Hey, any questions on that? All right, so next section we'll look at is 4.1, and this is on rational functions and asymptotes. So basically, a rational function is made up of two things that we've already studied. It's two polynomials, except now you're dividing them. Okay, so suppose f of x is a rational function. That's equal to p of x over q of x, where p of x and q of x are both rational polynomials. Now, we've got to be careful with q of x because it's in the denominator. What's the one thing we have to be careful about with q of x? It's a polynomial. It's in the bottom of a fraction, so it can't equal 0. All right, so now when we start talking about domain again, we're going to go back to having restrictions on the domain. Polynomials by themselves don't have any restrictions on the domain. But take a polynomial, throw it in the bottom of a fraction, now you do. Okay, you've got to make sure the denominator is never equal to 0. Okay, which basically means we're going to go back and do something we learned in chapter 3. We have to make sure we find the roots of the denominator. Okay? Anything that causes the denominator to be 0 is not a value that's in the domain. Okay, these are both examples of rational functions. Okay, and I'd say if you look at the top one, you should be able to tell pretty quickly what value you are not allowed to use in the domain. There's only one. Does anybody see?
3.
Yep, 3. Okay, you can't use 3. Bottom's a little harder, but we found roots of quadratics plenty of times. What's a way you could definitely find the roots of a quadratic if you had to? It works every time. Yeah, you can always just use the quadratic formula and find the roots. If they come out imaginary, we don't have to worry about it, okay? Because we're only worried about real roots. Or if you can factor it, sometimes that works too. Okay, we'll do a couple, but I just wanted to show you these, just examples of rational functions. Okay, it's two polynomials divided. Okay, so the domain of a rational function, you can use any number that you want as long as it never makes the denominator 0. That's the only restriction that you have. So let's, I think this is the one I just had on the other page. X squared plus 1 over x minus 3. So we actually already did it. Okay, Dave told us the domain here was all reals except 3. Okay, so I could write it like that. All reals except 3. Or does anybody remember how you do that as an interval with the u in between the two? So go ahead. From what to what? So negative infinity up to 3. Yep. And then 3 to infinity. Okay, so on the test, especially multiple choice questions, they tend to use that interval notation. So make sure we still remember that. If it was a short answer question, you could always just write it either way. These are all reals except 3. So if you were to graph this, something funny is going to happen at 3. All right, we've talked about discontinuities before. You can have breaks. You can have holes in the function. So we're going to have to see what's actually happening at 3. Okay, but there's something that's going to cause a discontinuity. So this is not a continuous function, okay, because 3 is not in the domain. All right, let's try this one. Okay, I already gave you a hint about it. What makes this one a little harder to find the zeros right away? And the top one was a little easier, but why is this one a little harder? Oh, Trevor? Yeah, it's a quadratic, so it's a little bit more complicated than a linear function to find the roots. But we can try to factor it. And if it factors, that's great. So we could try x and x. What would my signs have to be?
Plus and minus.
Yeah, plus minus. It doesn't matter which one you put where. Now, two numbers that multiply to give me 2 and subtract to give me 1.
2 and 1.
2 and 1, and it does matter which one we put where. How do you want to do it, Dave?
Me? Plus 2 minus 1.
All right, let's try it. So you get x squared minus x plus 2x is plus 1. So that's perfect. Now we can more easily tell what are the 2 roots to this because we factored it. Okay, so what Rachel, what are the 2 numbers here that would make the denominator 0?
It would be -2 and 1.
8. So my domain, I'm going to write it as an interval. So I can't include -2 and I can't include +1. So pick anything from -infinity to -2, or from -2 to 1, or from 1 to infinity. Right? Or you can write out all real numbers except -2 and +1. So if we were to graph this one, this graph is going to be in 3 pieces. Right? We're going to get 3 separate sections in this kind of graph. Okay? Because it has 2 breaks in it. Or they could be 2 holes or 2 something that's causing it to not be continuous. Okay, and this one I think actually it's a little easier than the last one. Kayla, what would be my 2 roots here? Or what would be my 2 values not in the domain? Yeah, you can't use 2 and you can't use -4. Okay, so domain. We can't use -4. And we also can't use, what do we say, 2. Okay, any questions on that one? Okay, we still haven't answered the question. So what's happening at 2 and what's happening at -4s? Do we have what's called an asymptote? Do we have a hole in the graph? What's happening? So we're gonna start to look at that in just a bit. All right, so the simplest kind of function you can have, it's called the reciprocal function. It's just 1 over x. Okay, 1 is a polynomial, x is a polynomial. And that's the simplest one you can have. So let's take a look at it. Let's graph it. And there's a few interesting things about it we'll take a look at. Okay, first of all, just to kind of make this graph a little clearer, this section does keep going down forever. And this section keeps going up forever. So there's the graph of 1 over x. Now that we've graphed it, I think it's really clear that it is not continuous. There's definitely a break in it at the value that would cause the denominator to be 0, which is 0 in this case. And let's look at what happens as x approaches infinity or negative infinity. What is f of x getting closer to? As x approaches infinity, what does f of x approach? Yeah, Al?
It approaches 0, but it'll never hit it.
Yeah, it approaches 0, but it'll never hit it. Just think about plugging bigger and bigger numbers in for x. What's happening to y? Well, if you plug in 10, y is 1/10. If you plug in 1,000 for x, y is 1/1000th. If you plug in 1,000,000, y is 1/1,000,000th. So it's getting smaller and smaller, the y value, as x gets bigger and bigger. Okay, what about as x heads towards negative infinity? Well, Tom, what's the y value approaching there? It's also approaching 0. Yep. 1 divided by negative 1/10 is negative 1/10. 1 divided by negative 1,000, negative 1/1000th. So it's getting smaller and smaller. But the way it's approaching 0 is from 2 different directions. Okay, the right section is approaching 0 coming down at it. The left section is approaching 0 by coming up at it from the negatives. Okay, coming up. And if we look at what happens as x gets really, really big, either in the positive or the negative direction, if there's a number you're getting closer and closer to, like in this case 0, we call that a horizontal asymptote. It's a value that you never reach on the y-axis as x gets bigger and bigger. Okay, so to find a horizontal asymptote, basically examine your y value as x heads towards infinity or negative infinity. So I said to you that it's a value you never hit on the y-axis as x gets really big. Okay. Both of those are examples of asymptotes. Now, this first one, you do actually cross the asymptote. You can cross asymptotes. But what I'm describing here is not the behavior near the origin. I'm talking about as you head farther and farther away. Is there a value you're getting close to? Even if you already crossed it once, that's fine. But are you getting closer and closer and closer? If you are, then that's an asymptote. You cannot cross your asymptote as x gets really, really big. So if I did this, then that dotted line I just drew in, that's not an asymptote anymore. Because I crossed it as x was getting bigger and bigger and bigger. Okay, and then sometimes you have one that's like on the left. It's a graph that it never crosses the asymptote. Either close near the origin or very far away. It's never crossing it. Okay, so any question on what an asymptote, a horizontal asymptote is? All right, so next what we'll do is I'll give you a couple functions and we'll look at what the horizontal asymptotes are. Okay, now first of all, a horizontal asymptote, it's an equation of a line. Right? It's an equation of a horizontal line. The equation of a horizontal line always starts out with what letter equals? Oh, is that, yeah? Yep, it always starts out y equals. Now we just have to figure out what it's approaching. What's happening here as you let x get bigger and bigger and bigger? What's my y value going to approach?
2.
2. Can you explain that?
Because that's your 2 is your y-intercept. So if you're making your x value bigger, getting closer and closer to that. No.
All right, well, just be careful when you say intercept, because that's not an equation of a line.
Okay.
So this graph might cross the y-axis, it might not. We don't know yet. But the key is, look at this. As you make this if you make x bigger and bigger and bigger, what's happening to this fraction?
Getting smaller.
It's getting very small, right? Pretend x is a million. Right? You've got 1 divided by a million. That's 1/1,000,000th plus 2. It's like 2.000001. All right, so as x gets bigger and bigger, this fraction that I circled just about disappears, and we get just y equals 2. Okay? Same thing if you look at it from the negative side. Take 1 and divide by -100 for x. That's -1/100th plus 2. That's 1.99. Okay, so it's getting closer and closer to 2. Go slow, it's over my head. Okay, any questions on that? Okay, another way to think about it is, well, if you have a reciprocal function, this is the normal one, and the y-intercept is at y, or the y-asymptote is at y equals 0. This plus 2 is a vertical shift up 2. Anytime you add a number onto the end, it takes everything and shifts it up 2, including the asymptote, which was at 0. All right. How about this one? What's going to be my horizontal asymptote here? Yeah?
-3.
Yeah, it's going to be y equals -3. Okay. Anything that has a variable in the bottom of a fraction, if you let that variable get huge, the fraction disappears. Okay, because you're dividing by a huge number. Okay, the only problem with that is if you have variables in the top and in the bottom. Because then you say, well, if there's variables in the top, then the top can get bigger and bigger. But if there are variables in the bottom can also get bigger and bigger. So then it's kind of a question of which one is getting bigger faster. Okay? Now it has to do with powers. So then we look at, is it an x squared in the top and an x in the bottom? But we're not quite there yet. Okay. So any questions on why your horizontal asymptote is y equals -3? All right. So let's graph this one, and let's graph it by hand. So when I graph it by hand, the first thing I like to do is just mark my horizontal asymptote, which we've already done. Okay, horizontal asymptotes, what you usually do is just draw a dotted line. Okay, that's your horizontal asymptote. Right? And what I do is like to try, let's just try a couple values. Like when x is 1. If I plug 1 in for x, what do I get for y? Yeah, I get 3. So 1, 3 is a point on the graph. All right, let's plug in 0.5. What's 1 divided by 0.5? 2 plus 2? 4. So at 0.5, we're up at 4. Okay, and what's going to happen, and we'll have a better idea of this in the next section, is this is just going to go up higher and higher and higher, getting closer and closer. Okay, in this section, we have an asymptote, so it has to curve, come down, get closer and closer and closer, but never cross. And we're going to have the same behavior kind of over in the quadrant, mostly quadrant 3 section. Okay, let's try plugging in, I don't know, let's do, what would be a good value to plug in for x? Yeah? Sure, we could do -1. 1 divided by -1 is -1. -1 plus 2 is 1. So -1, 1. Okay, we could also do -0.5. Okay, that would be -2 plus 2. That would be 0. So -0.50. It's almost like a mirror image, okay, of what we just had. As you get bigger and more negative, You could do like negative, let's do -2. Okay, that's -1/2 plus 2. What's -1/2 plus 2? What is it? -1.5. Right, so we got -1, -1.5. So you can start to see the curve. And it's basically going to go something like that. And down like that. Okay, so to graph these kind of shapes, you just got to try a few values close to, in this case, 0, because 0 is the value that I can't use, but try a couple close to it, and then try a couple further away to see that curve. Any questions on that one? Does anybody notice another kind of asymptote we have in this problem? We do have that horizontal one, but what else? Yeah?
Do you have a vertical one at x equals 0?
Yeah, there's also a vertical asymptote here. Okay, and we're going to talk about vertical asymptotes as well. Okay, most of these kind of problems will have both. Right, so what I want to look at now is I want to look at the same function we just had. And we're going to start to talk about the vertical asymptotes. I want to look at what happened as x approaches 0. But you can approach 0 from two different directions. Okay? You can approach 0 from the positive side, which means if this is a number line, this is approaching 0 from the positive side. Okay? Or you can approach 0 from the negative side. This is approaching 0 from the negative side. And what happens in this graph is that as you approach 0 from either direction, your y value approaches infinity or negative infinity. Okay? And we can test that by plugging in a number very close to 0, but not 0. Okay? Trevor, what's a number that's very close to 0? -0.1. How about even closer?
A lot of zeros and then a 1.
Okay, so like -0.01.
Sure.
All right, let's just try that. So what I'm doing is I'm plugging -0.01 in to that expression. Okay, and if I do that, I get -100. Okay, if I plug in 1 divided by 0.0001, that's even closer to 0. I get 10,000. Right? So as x gets smaller and smaller and smaller, okay, it gets very, very close to 0, the y value is approaching infinity or negative infinity. Any question on why that's happening here? Okay, we saw that visually, okay, in the last graph. And if this happens, this is basically telling you you have a vertical asymptote. So in this problem, we would say exactly as Ali said it, x equals 0 is a vertical asymptote. And some problems have multiple vertical asymptotes. Okay, so if you've got a couple values in the domain you can't use, you might have 2 or 3 or 4 vertical asymptotes. Generally, we don't graph any more complicated than having 2. What is 0 in this fraction? What do we call it back from chapter 3? 0 is the what of this expression? Specifically, just the bottom part. 0 is it's the root. Okay, 0 is the root of the denominator. So, in general, if you can find the roots of the denominator, that's where your vertical asymptotes could occur. Now, another thing that could happen besides an asymptote is a hole. Okay, you can also get a hole in the graph. And if you don't remember when you get a hole, I'll explain that again later, but not just yet. Okay, but if you notice this behavior happen as you get very, very close to your root of your denominator, all of a sudden your y value goes up to infinity or negative infinity. That's when you have a vertical asymptote. But don't always assume just because you have a root of the denominator that it's an asymptote. It's not. Okay, sometimes it's a hole. And the way you know if it's a hole versus an asymptote is right there. If the numerator and denominator do not have any common factors, then you get vertical asymptotes when you find the roots of the denominator. But if the numerator and denominator did have a common factor, that's when you get a hole in the graph. And let me show you. Let me graph, scroll that up a little for you. For some reason my calculator, I can't, sometimes all of a sudden I just can't click on it. So then I have to minimize it, just move it, put it back up, then I can click on it. All right, so let me graph something like x plus 2. And I'm not going to FOIL it out. I'm just going to leave it factored. Times x minus 3. And I'm going to divide that by x plus 1. Are there any common factors in the numerator or denominator there? Oh, Amanda? Nope. What's the root of the denominator? -1. Since there are no common factors, you will get a vertical asymptote at -1. That's exactly what I had. I could draw a dotted line in right there. Now, there's another asymptote in that picture too called a slant asymptote, but I'm not going to focus on that for now. Are there any common factors in the numerator and denominator now? Yeah, x plus 1. So the root of the bottom is still -1, but because there's a common factor in the numerator, you are no longer going to have a vertical asymptote. You have a hole in the graph. And it basically looks like the graph y equals x minus 3, a line with a slope of 1 and a y-intercept of -3. And if I showed you that graph without showing you the equation it came from, you can't tell there's a hole. The only way I know there's a hole is looking at the original. And if I try to trace to -1, I can't. There's no y value. Okay, so there's an error, but it's not an asymptote. Okay, so any question on when you have an asymptote and when you don't? All right, so let's see if we can find our vertical asymptotes here. Okay, so look at the denominator, find the roots, and then ask yourself, do I have a common factor in the top and in the bottom? If no, then the root is a vertical asymptote. Okay, so Grayson, what's the root of the denominator here? 2. Do I have a common factor in the top and the bottom? No. Then 2 is a vertical asymptote. Okay? If I had an x minus 2 in the top, it would not be. So how do I write 2 as the vertical asymptote? What's the equation of the line? And remember, this is vertical, not horizontal. Oh, Pacey? Tell me.
X equals -2.
So Gracie, can you remind us again, where did you say the root was? What number? 2. So it's going to have something to do with the root, which is 2. Just on double check. You said negative 2, right?
Would it be x equals positive 2?
Yeah, it would just be x equals positive 2. That's the vertical asymptote. Okay, and another way to look at it is when you... Any questions on that? All right, so I could go back and graph this one just like I did the other one. Does anybody want me to graph this by hand? Show you how everyone feels, because there will be some on the test you have to graph, and I'll look for certain points by hand. Okay, sure. I'll just show you real quick. So generally, when you graph it, first thing I always do is graph my asymptotes. Okay, I know there's a horizontal asymptote at y equals 0. Okay, I know that because if I let x get really, really big, this fraction gets very close to 0. Okay, and now I know there's a vertical asymptote at x equals 2. Once I get those asymptotes, it basically kind of gives me boundaries of where to put my curve, and I know it's going to be in 2 sections. Okay, this type of graph. Okay, so what I do is I try a really big value. Okay, let x be like, I don't know, 100. 100 minus 2 is 98. 1 divided by 98, that's extremely small, but it's still positive. So I'm going to be about there. And then try a value very close to 2. Let's try a value just to the right of 2. Tom, what's a value just a little bigger than 2? But very, very, very close.
2.01.
Sure, 2.01. What's 2.01 take away 2? 0.01. And now if I take 1 and divide by 0.01, I get a huge number. Okay, so I'm way up here. All right, so we got our 2 points, okay, by doing the kind of the upper right section. So it's going to come down, it's going to curve, kind of do something like that. And now I'm going to get 2 points in the other section. So I'll try like negative 100 for x. Okay, if I do that, negative 100 minus 2 is negative 102. And 1 divided by negative 102 is an extremely small number, but still negative. Okay, now try a value very close to 2, but this time on the left of it. Okay, like 1.99. So in my head, if I do 1.99, take away 2, that's negative 0.01. Okay. If you take 1 divided by negative 0.01, it's way down. Okay. So that's how I graph every rational function. Try a value just to the right of the asymptote, just to the left, and then try a value really big for x and really small. And it'll give you these 4 points. And remember, they have to be connected, and it's curved. Okay, so, and it's got to kind of get closer and closer to those asymptotes. Okay, any questions on that one? All right. So let me put that one up for a second and give you guys a second to look at that. And I want to look at how I can transform this into that. Okay, the problem is it's not written the way we need it. Okay, generally you need it like something like this. If you want to know how it's been transformed, you have to have 1 divided by, and then you can have x plus or minus a number, and then plus or minus a number at the end. This one's not written that way. So take a second and see if you can remember something we did back in chapter 3 that could help us to actually do this out and rewrite it. Okay, so just take a second and think about that. Okay, so any thoughts on how I can do this out? Something we learned back in chapter 3 that would help us out? Oh, okay, so you're thinking, yeah, when you have imaginaries in the bottom, you can multiply by the conjugate to get rid of the imaginaries. In this case, we don't have any imaginaries, so we're not going to use a conjugate. But how can I do this out? What did we learn? Like, what operation am I doing here? I'm doing division. So can I divide two polynomials? Is that something I can do? Well, hopefully remember how to do. Yeah, okay. You have two choices. You could do synthetic division, or you could just do the regular long division. It's not that hard to do the long division here because the numerator and denominator both have exponents of 1. So you're only going to have to really do it one time. So let's just do the regular long division. And how many times does x go into 2x? Or what does that leave me with? Yep, 2. Multiply back out. 2 times x. What's 2 times negative 5? Negative 10. And subtract. What's negative 13 minus 10? Let's see. Yep, it's going to leave me with, well, careful, not 3. Negative 3. All right, so now I basically have what I need. Okay, 2 is my what? When you divide two things. That's my quotient. So remember, it's quotient plus remainder over divisor. Okay, that's how you always write your answer. Quotient plus, what was my remainder? So yeah, I really could have put minus this time. I'll fix that. Quotient plus remainder over, and what was my divisor? X minus 5. Okay, let's just, we can write that a little nicer. Let's write it as negative 3 over x minus 5 plus 2. Now I can clearly see the two shifts. Okay, I've done a left and a right, and an up and a down, and now I can figure it out. So that's your first step. Okay, rewrite it. And now, where is my horizontal asymptote? As x gets bigger and bigger, what number is this expression going to approach? Rachel?
2.
Yeah, it's going to approach 2. Okay? Because as x gets bigger and bigger, that fraction is going to be wiped out because you're going to divide negative 3 by a huge number. So we get y equals 2 as my horizontal asymptote. And what about my vertical asymptote? Look for the undefined values, and then ask yourself, do you have common factors? Okay, so Trevor, what's my vertical asymptote? Yep, and we just want to make sure we write it x equals 5. And I don't have an x minus 5 on the top. There's no common factor. Okay, so if you get a problem that's not written in the way that it should be, you might have to do long division. You could have done synthetic division if you like that better. Rewrite it. And then you can figure out your asymptotes. Okay, any questions on what I did there? Just as a reminder about the long division, if you're missing any terms, make sure you fill in zeros for anything you're missing. Okay, that didn't happen here, but it could. Okay, and I think next year will be our last problem. So we've done these kinds of problems before, but we're going to look at them a little differently. So just to kind of start us off, if I told you you had an acid solution, you have 50 ounces, and it's a 35% solution. Let's say the rest of it is water. So you have 50 ounces, only 35% of it is actually acid. How do you find out how much acid is in that 50 ounces? If only 35% of the 50 ounces is actually acid. Jeff?
When you multiply 50 by 0.35?
Yeah. If I tell you you've got 50 ounces, but only 35% of it is acid, just take 50 times 0.35, and that tells you in this thing that you must have mixed 17.5 ounces of acid, and the rest was water, or whatever. Okay, so that's an important idea that you need to make sure we understand that to do what we're going to do. So in this problem, what we're going to do is we're going to take X ounces of pure acid. Okay, we don't know how much. We're going to take X ounces of pure acid, and we're going to add it to the solution we already have. Okay, so pure acid, it's 100% strength. And we're going to add it to the current solution. Okay, and the first thing I want to do is find a graph of the new concentration of acid. Okay, depending on how many ounces of pure acid you add. So when you want to graph the concentration, how do you figure out the concentration of a solution? You have to divide two things. Like if I told you, here's a solution, there's 40 ounces, only 10% of it is acid. Or I'm sorry, let's do it this way. You have a solution that's 40 ounces, 10 ounces is acid. How do you figure out the concentration? 40 total ounces of solution, 10 ounces of pure acid in that solution. What do you do to find the percentage? Divide. I like the idea of dividing, but I just have to be careful how we divide it.
Divide the amount of acid you have by the total amount of acid.
Yeah, divide the amount of acid, which would be 10, divided by the total, which I said was 40, and that tells you it's 0.25 or a 25% solution. Okay, so let's keep that idea in mind. Take the amount of acid divided by total amount of solution. So that's basically the formula you have to set up. So it says, let's start off with the fact we have a 50-ounce solution and 35% of it, 35% is acid. So what's the amount of acid in our solution right now? How much?
17.
Yeah, so we have 17.5 ounces of acid, okay, in our solution. That's the amount we have. And how much acid am I going to add to that? I'm going to add X ounces. Okay, so my numerator now represents the total amount of acid in the solution. And now my denominator has to be the total amount of solution. Okay, how much solution are we starting with? We're starting with 50 ounces. And how much are we adding to the solution? X. Okay. There's my concentration as a function of X, how many ounces of acid I add. Now, as you add more and more and more pure acid, what's going to happen to the concentration of the acid? Yeah?
Higher and higher and higher.
It's going to get higher and higher. Is there any limit that it's going to approach?
It's not going to
It's not going
be 100.
to be what?
It's not going to be 100
Why can't it ever be 100?
because you still have some of the acid that isn't actually acid.
Right, you still have some of the original solution that was not acid to begin with. So no matter how much acid you add, it will never reach a concentration of 100%. It can't. All right? So now I want to figure out how much acid do I have to add to get it up to a 75% concentration. Well, first of all, let me graph the concentration. So 17.5 plus X divided by 50 plus X. And now let's use some values. What's a minimum value for the acid I could add? What's the smallest amount that would make sense? Oh, Quinn? Well, just think logically, like if you were actually doing this, what's a value that wouldn't make sense to add for acid?
0.
You could add 0, which just means you don't add anything to it. But what can't you add?
Negative.
Yeah, you can't add negative amounts of acid. That doesn't make sense. So for our window, let's not look at negatives. The maximum amount of acid, there is no maximum. Depending on how much materials you have, but you could add as much as you want. So let's go up to 250. And Y is our concentration. What's the minimum the concentration is ever going to be? Well, 17.5 is how much acid is in the solution, but that's out of 50. So what concentration was that? 35%. It's as low as the concentration can get because you're not adding water to it, you're adding acid. And what's the highest it could get? It could be 100, but we've got to be careful. It's not 100 on Y max. What would you put in for your Y max? No, not 10. That's too high. How much? It'd be 1, right? These are your decimals. Okay, so anywhere from 0 to 1 is the concentration. And in our problem, it's really 0.35 to 1. So graph it. There's your concentration as you add more and more acid. So you can see at first, if you start adding acid, it brings the concentration up quick. But over time, if you want to keep raising it higher and higher, you have to add tremendous amounts of acid to get it higher and higher. All right, so I want to know when the concentration is going to be 75%. So how could I use my graph to do that? I mean, I could kind of trace and, try to look for where Y is 0.75, but I'm never going to get it exact. So what could I do?
Couldn't you make a line going to 7.75
Mm-hmm.
and then calculate the intercept?
Yeah. So see where those two cross, and it's exactly what we did in the last section. Wherever they cross, that's how much acid I need to add to get it to 0.75. And so the answer, 80 ounces. If you didn't have a calculator and they asked you to solve it algebraically, all you have to do is fill in 80 for that left-hand side. 80 equals 17.5 plus x divided by 50 plus x. Okay, and you would start by multiplying both sides by 50 plus x. And you'd have a couple steps. You'd have to bring all your x's to one side and bring all your numbers without x's on the other. But it's just basic Algebra 1 equation. Any questions on how you'd solve that if I asked you to do it algebraically? And if you solve it, you should get, oops. You wouldn't know the answer before you start. You'd fill in the concentration. Okay, so that's your concentration. C, concentration. But now it's still the same steps. Distribute it out, move all your x's to one side, get it by itself. You should get 80 for x. Okay, so any questions on that one? So you saw by adding 80 ounces, it brought the concentration all the way up from, was it 35 to start? Yeah, it brought it from 35 to 75. If you add another 80 ounces, it's not going to bring it up nearly as much. Okay? It's going to really start to slow down because it levels off. And I'll put that picture in the notes so you have it. All right, so I think that's a good stopping point for today. All right, so the homework, it's over 2 pages. The first one this is 3.7. So it's page 207, numbers 8, 9, 10. Those are all just calculating intersect, so those are very quick. And then 4.1, that's page 222. It's 3 to 7, odd. 11 to 21, odd. 23, 31, 37, 38. And 48, just parts A and B. I think there's a part C, but you don't have to do that. Just A and B.